Good afternoon, dear students. We are doing sequence and series, right? We have earlier discussed arithmetic uh, progression. That we have discussed about the common difference, and we are doing the geometric sequence, also known as GP, geometric progression also, and we have studied that the nth term of the geometric sequence, that is a into r n minus 1, right? So every term that is multiplied by a fixed number, that is called common ratio. That r is here the common ratio, right? Common ratio, right? Like in AP we are going with common difference. Here we are going with the common ratio. Okay, that is geometric progressions. Okay, so Jaswinder ji, very good morning. So let's discuss some questions. We have discussed last time also some questions. Find the seventh term of the geometric sequence. Let's discuss here. Find the seventh term of the find the question is find the seventh term of the sequence of GP whose terms are sequence 8, 24, 72, 216. So here what we have the first term a is equal to 8 here, right? And what is the common ratio here? The value of r, that is the value of r is equal to 8 into 3 is 24, 24 into 3. So value of r, that is the common ratio, that is 3. Now we will apply the formula that uk is equal to that kth term, that is equal to your a plus a, that is first term, r raised to power k minus 1, one term less, or u a n is equal to a plus r raised to n minus 1, right? So here we will put this value. First term is a is 8, and the common difference, that is 3 raised to power n, n is 7 minus 1, 6. So we have 8 into 3 raised to power 6, right? So after multiplying we will get that the seventh term, that is 5, 8, 3, 2. 5, 8, 3, 2 is the seventh term of this, right? So in this way we can find the nth term of the geometric progression, right? Now we will switch over to, like we are doing in arithmetic progression, sum of n terms. So here also we will discuss sum of, that is the sum of the terms of the sum of the terms of geometric progression, right? Sum of the terms of geometric progression, right? So here, suppose we have one example here, that is 1 plus 2 plus 4. If I am talking 1 plus 2 plus 4 plus 8 plus so on 16 plus dash 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 2 raised to power 63, right? So here this is geometric series, right? This is what? This is a geometric series. Geometric series. When we are adding, then it becomes series. Okay, so we have discussed what is sequence and what is series, right? So here 1 plus 2 plus 4 plus 8 plus 16 plus then 32 so on. Okay, the common ratio is 2 here, right? So here we want the sum of this sequence. So we are saying call this series as S. Call this series as S. S is equal to 1, right? 1 plus 2 plus 4 plus 8 plus so on up to 2 raised to power 63, right? We have explained the sum by this example. Now multiply this throughout by 2. This equation multiplying throughout by 2. What we get? That is y is 2. The common ratio r here is 2. Common ratio is 2. So multiplying this whole equation by 2 we get 2s. Here we get that is 2. Here we get 4, 8, so on, 16, and so on. Here 2 raised to power 64. Right? When we what we have done, this equation, that this is equation number 1, right? And this is equation number 2. Now, what we will do? We will subtract 1 from 2. Subtract 1 from 2. Subtract equation 1 from 2. When we subtract the equation, right? Here, so that is S, that is 1 plus 2 plus 4 plus 8 plus 16 plus so on here, that is 2 raised to power 63, right? So here that is 2 raised to power 63. So here when we subtract here, what we will get? Minus. So here we will get S only. S is equal to 1. So it is minus here, minus of 1. And here everything is left plus 0 plus 0 plus 0 plus 0 so on. And we have left here 2 raised to power 64. Right? So we can write here that the sum is 2 raised to power 64 minus 1, right? 2 raised to power 64 minus of 1, and here approximately its value, which is about its value is 1.85 into 10 raised to power 19, right? This is the approximate value of this one. So here what we have done, first this equation is there, common ratio that is 2, so we have multiplied the whole equation by 2, right? And this is the first equation and this is second equation, subtracting 1 from 2, right? So 2 and 2 get cancelled, 4, 8, so on. So we have left here, that is S is equal to minus 1 plus that is 264 raised power 64. So we have the answer, that is 2 raised power 64 minus 1. That is the sum of these n terms, right? So next we have one more this equation, right? That is the sum of here find the sum of find the sum of find the sum of find the sum of 0.2 plus 1 plus 5 plus so on plus 390,625. Okay, so here in this geometric progression the common ratio is 5, right? What is the common ratio here, right? R is equal to 5 here, right? So let's take, we will take first let S, right? That S is equal to here 0.2 plus 1 plus 5 plus so on, that is passes plus 390,625. Okay, so here common ratio is 5, so we will multiply this equation by 5 both sides. This is equation number 1. This is equation number 1. So we have here 5s, 5 times s is equal to, right? That is 5 20, that is 1 5 25, 1 5 25, so on, and the last, that is 390,625 plus last is 195,3125. This is equation number 2, right? So subtracting 1 from 2, subtracting equation 1 from 2, subtracting equation 1 from 2, 1 from 2, we get here 5s. So here when we subtract 1 with 1, if one equation is there, right? So here we will 5 1 with 1 get cancelled. Sorry, here we will 1 with 1, right? So here when we get 4s is equal to 4s is equal to minus of 0.2 plus 0 plus 0 so on plus, that is 195,3125, right? So what is this gives that s is equal to that is after subtraction we get first 4s is equal to 1953124.8 and s is equal to, this implies that s is equal to 488,281.2. This is the sum of, right? So here the same method can be applied to general geometric progressions to give the formula, right? The same method we will apply, right? For the general method, if we have a sequence that is Sn, sum for the sum of n terms, that is equal to a plus ar plus AR square plus AR cube plus so on, that is equal to last term, that is AR raised to power n minus 1. Right? So this is the first equation. This is the first equation. Now here R is the common ratio, so multiplying, that is R with Sn, right? What we will get? We will get AR plus AR raised to power 2 plus AR raised to power 3 plus AR raised to power 4 plus so on, right? The last term, it will be A raised to power Rn. This is equation number 2, right? So subtracting equation 1 from 2, right? Equation 1 from equation 2, what we get? We get here S, right? When we subtract 1 from the 2, it gives that S R minus 1 into Sn is equal to minus of A plus A raised to R raised to power n, right? Here we are, it is, right? What I have written, if it is S R S n minus Sn, how I have written? I have written here R minus 1, Sn is common, Sn is common, and here is R minus 1, right? This is Sn when subtracted from Rsn, so it is R1, R minus 1 into Sn, and here it is rest everything is corrected, minus A is left, and A raised to A, R raised to power n is there. Okay, so here what is sum of the n terms? So here we can write, that is A into R raised to power n minus 1. This can also be written as A into R raised to power n minus 1, right? And Sn can be written as, that is divided by R minus 1, right? So this is the formula for the sum of the n terms of the GP. That is, right? So here this can also be written as, Sn is written as, that is A into 1 minus R raised to power n upon 1 minus R. Both are one and same. Here 1 into A is equal to R raised to power n minus 1 into R minus 1, or here, because sign both numerator and denominator will remain the same. So in both ways you can write it. Okay, there is sum of n terms of the GP. Okay, so here they have taken the consecutive. If three terms are in geometric progression, if three terms if three terms there are, if three terms are A, B and C, A, B and C are are in geometric progression, right? If these three terms A, B, and C are in geometric progression, then we have B square. B square is always equal to AC, right? If three terms A, B, and C they are in geometric progression, then always the middle term, the square of middle terms is equal to the product of the extremes A into C. Okay. Next, we have here, because what is A? A is equal to B upon R, that is the common ratio. So here, what is C? C is equal to BR, right? So means what is AC? Here, AC is equal to your BR into BR, right? Common ratio. So here R and R get cancelled. So we have B square. AC is equal to B square, right? Always in geometric progression, three terms they are in geometric progressions, and middle term, square of middle term is always equal to the product of these A and C, right? So let's take some for some infinite geometric progressions, right? Some infinite geometric progressions, right? Infinite geometric progression. So here, like we have the sequence like 1 plus 2 plus 1 upon 4 plus 1 upon 8 plus 1 upon 16 plus so on, right? No last term, that is your terms as infinite geometric progressions. Here the common ratio R is 2. Common ratio, that is half, right? Half of 1 is half of 1 by 4, its half is 1 by 8, its half is 1 by 16, right? So this geometric progression is infinite because we have no last term. So go on, it will be 1 upon 32, 1 upon 64, so on. Okay, so this kind of the sequence or this kind of series here is geometric series. Okay, so let's see one more we have here, that is if it starts from 1 by 2, right? Then 1 by 4 by 3, so on, 1 8 by 7, so on, 1 15 by 16, so on. So here also it's clear that the we get the nearest sum gets to 3 to 2 here in the limit. So what is here? The n approaches to infinity as n approaches to 2. In this case, if n approaches to infinity, right? If n approaches to infinity, the sum of n terms approaches to, that is 2, right? If the value of n approaches to infinity, here in both these sequences, if the n approaches to infinity, the Sn approaches to 2, right? So in both these, and both these examples are examples of convergent series, convergent series, right? Right? Convergent series. So the sum to infinity is a finite number. What are the convergent series? The sum of infinite numbers, sum of infinite numbers, the sum of infinite numbers is a finite number, finite number, finite number. So here we have infinite numbers 1, 1 upon 2, 1 upon 4 plus 1 upon 8 plus 1 upon 16 plus so on. Right? So these two are the examples of convergent series. These are the examples of convergent series. Right? So here what we have, by if we are using here sum of n terms is equal to, that is a into 1 minus r raised to power n multiplied by 1 minus r here, right? So we can find these here, these sequences. If in one case that r is 1 by 2, here the first term, that is 1 into 1 minus, that is 1 by 2 into n upon, that is 1 minus 1 by 2, right? So here when we solve, we have 2 into, that is 1 minus 1 by 2 raised to power, here it is n, right? So here we can go on finding. They have discussed a beautiful method here, graphical, like here. This is 2 units, right? This is here 2 units, right? So 1. This is 1. Then they are giving 1.5. It is 1.5. Is 1. Then 1/4. This is the 1/4. Then 1/8. 1/8. Then this is 1/16, right? And so on. 1/32. So on, dividing. Then this is half. Then it's again half. Then again half, half, and so on, right? So here the value is 2. The sum, that is 2 here. So this, the condition for the divergence is that r have value -1 to 1. So here we can write that for the infinite sequence, S infinity is equal to, that is equal to a upon 1 minus r, right? What is it? A minus 1 upon a upon 1 minus r, right? So for the condition for the geometric series to converge, right? The condition for a geometric series to converge -1, the ratio that is lies between -1 to 1, right? So that when n approaches to infinity, then r is equal to n approaches to 0. right? When n approaches to infinity, r is for n approaches to 0, right? So here we have one question: find the sum of the terms of the infinite progression, right? Question is find the sum of find the sum of the infinite series. Find the sum of the terms of infinite series of progression 0 point series infinite progression, that is 0.2, 0.02, 0.002, so on, right? You have to find the sum of the progression, right? Thus the geometric progression a and r. Here solution here. What is the first term? First term is 0.2. 0.2, 0.02, 0.002, so on. And what is the common ratio? Common ratio here is 0.1. R is equal to 0.1. So here this is the infinite progression. And for infinite progression, right? Sum of the infinite progression, that is equal to A upon 1 minus R. Right? What is the sum of the infinite progression? That is sum of, it should be convergent 1, so 1 minus r. So here sum of infinite sequence, that is a 0.2, 1 minus r. So r is 0.1, right? So we have here the answer is that is 0.2 into 1 minus 0.9. So here, sorry, 1 minus 0.1 is 0.9, right? So what we have, sum of infinite, this progression is 2 by 9, right? This is the answer. That is 2 by 9. So here we have one more question, right? Let's take the question. So question is, the first three terms of infinite geometric progressions are 16, 12 and 9. The first three terms of the geometric progression are 16, 12 and 9, right? The, the three terms of geometry 16, 12 and 9, write down the common ratio and find the sum of the terms of the progression, right? Find the terms. So here, first is we have to find the common ratio, right? And second, we have to find the sum of the terms of the progression. Sum of the terms of the progression. part 1, common ratio here is common ratio, right? So common ratio can be divided, or sorry, multiply 16 with, that is 3 by 4. So what is the R here? The common ratio R is equal to 3 by 4. Now the sum of the progression, that sum of the progression that is equal to same A plus 1 minus R, right? What is A? A is 16, and what is 1 minus 3 by 4? So here the answer here is 16 into 4, 4 minus 3 is 1, so answer here is 64. Sum of the sequence here, that is the series, sorry, that is 64 here. Okay, so this is the sum of the n terms of this progression here. So we have the exercise, right? So you can go through the some questions here related to the geometric progressions. So tomorrow we will discuss about the binomial expansion, right? Tomorrow we will discuss about the binomial expansion, right? So we will discuss about the binomial expansion, right? So this is all about today's class, right? So you can solve the questions from both your arithmetic progressions and geometric progressions, right? So with this, thank you very much. God bless you all. Stay safe and stay healthy.